Okay, let's just dive right into this. Welcome to today's Explainer, where we're going to trace one of the most incredible, totally invisible journeys happening all around us every single day. We are going to follow the exact path electricity takes, starting from the massive turbines of a power generation plant all the way to the outlets right there in your living room. It's an absolute marvel of engineering, and I am so excited to break it all down with you. I mean, think about it for a second. Every single time you switch on a light, electricity reaches your home in a literal fraction of a second. It feels instant, right? It feels totally simple. But the reality is that the electricity illuminating your room right now just traveled hundreds of kilometers through a highly complex, carefully balanced network. So have you ever actually wondered where that specific spark of power came from and the absolute gauntlet it had to run just to charge your phone or turn on your TV? Well, here is our roadmap for today's Explainer. We'll start right at the source with generating the power. Hit the high-voltage highway, pass through substations and grid control, navigate the local distribution network, and then finally, enter your home. All right, step one, generating the power, creating the spark. So whether we're talking about a massive thermal power plant using steam, a hydro plant harnessing a waterfall, or a giant wind farm, the core magic here is a concept called electromagnetic induction. Basically, a massive turbine converts mechanical energy into electrical energy by driving a generator. The electricity generated here is typically pumped out at around 11 kilovolts, and it operates at a super strict frequency of 50 or 60 hertz, depending on what part of the world you live in. And this generation is governed by incredibly strict international standards to make sure everything is absolutely safe and consistent right from the get-go. Now, what's really interesting here is that generators don't just spit out a flat, continuous line of power. They actually produce what we call three-phase alternating current, or AC. Because these three overlapping waveforms are perfectly out of phase with one another, whenever one wave drops to zero, the others are actively providing power. It's like a perfectly synchronized dance. And this three-phase system is incredibly efficient for generating and transmitting huge amounts of energy really smoothly over massive distances. Moving on to part two, the high-voltage highway, where we transmit all this power. To really wrap our heads around this transmission phase, we need to understand the relationship between voltage and current. And honestly, the best way to do that is to picture a water pipeline. Think of voltage as the water pressure pushing through the pipe, and think of current as the actual physical volume of the water that's flowing. Now, if we try to push a massive volume of water, meaning high current, through a pipe, there's going to be a ton of friction. But if we crank up the pressure, the voltage, we can move the exact same amount of total energy with a much smaller physical flow. But why are engineers so obsessed with reducing that physical flow? Well, it comes down to a crucial concept: I squared R losses. Basically, as electric current flows through any wire, it fights against resistance, and that friction generates heat. That heat is entirely wasted energy. And because the current, represented by I, is squared in this formula, even a tiny increase in current causes a massive exponential increase in wasted heat. So to push power over hundreds of miles efficiently, we literally have no choice but to lower the current. And we do that by stepping way up on the voltage. Let me put this into perspective for you, because the contrast in efficiency here is just awe-inspiring. Imagine we tried to transmit a 100 megawatt load at our starting generation voltage of 11 kilovolts. We'd have to push over 9,000 amps of current. The heat losses would be absolutely catastrophic. The cables might just melt. But when we use a step-up transformer to boost that voltage to 400 kilovolts, the current plummets down to just 250 amps. And those line losses? They drop to a microscopic 0.08%. This right here is exactly how we make long-distance transmission a reality. So the absolutely crucial point to take away is this. By stepping up the voltage from 11 kilovolts to 220 kilovolts, the wasted energy drops by a staggering 400 times. It perfectly highlights the absolute magic of step-up transformers. Without them, trying to move electricity across a country wouldn't just be expensive, it would be physically impossible. So what exactly is all this power physically traveling on? Well, those massive metal towers you see along the highway are holding up overhead transmission lines. And these aren't just solid copper wires hanging up there. They typically use what's called ACSR, aluminum conductor steel reinforced cables. It's a brilliant engineering compromise, really. The aluminum is superconductive and lightweight, letting the electricity flow easily. Meanwhile, the steel core running down the middle provides the immense tensile strength needed to support those crazy long spans between towers. That way, the heavy wires don't sag dangerously close to the ground on a hot day. To sum up this entire stage of the journey, a lead systems engineer at the National Grid actually put it perfectly. Without transformers, every segment of the grid would be an isolated island. Transformers really are the ultimate enablers of our modern world, linking the isolated island of a remote power plant to the massive continent of consumer demand. Which brings us to part 3, substations and grid control, the strategic checkpoints of our journey. Think of substations as the off-ramps of our high-voltage highway. We don't just suddenly drop the voltage all at once. It works in a progressive scale-down arc. We take that incredibly dangerous 400 kilovolt transmission line and step it down to a 132 kilovolt primary substation for a whole region, then down to 33 kilovolts for a secondary city substation, and finally down to 11 kilovolts for local distribution. This gradual reduction is absolutely essential to ensure stability and, most importantly, safety, as all this power moves closer to where people actually live. But, substations do a whole lot more than just step-down voltage. They are essentially the protective brains of the electrical grid. They're packed with gas-insulated switchgear, high-voltage circuit breakers, and digital protection relays. These components are designed to act in mere milliseconds to isolate faults, like say if a tree suddenly falls on a power line, preventing a massive cascading blackout. Meanwhile, advanced SCADA monitoring systems are giving engineers real-time visibility into the grid's health so they can route power strategically exactly where it's needed. Next up, part 4, the local distribution network. We are officially in the final mile.
Now, you are definitely familiar with this part of the journey, even if you don't realize it. Those 11 kilovolt distribution lines, those are the ones running right along your residential streets. But obviously, 11,000 volts is still way, way too high to bring into your living room. That's exactly why you'll see those gray cylinders mounted up on utility poles or those big green metal boxes sitting on the ground in your neighborhood, the pad-mounted transformers. These guys are the final gatekeepers of safety. They perform the very last step down in voltage right before the power crosses onto your property.
And finally, part 5, entering your home, safe and ready to use. This final connection is just such a brilliantly clever piece of engineering. That utility pole transformer uses something called a grounded center tap on its secondary side to literally split the voltage. This specific design gives us the standard, much safer 120-volt circuits that we use for our lights and regular wall outlets. But at the same time, it allows the outer two ends to combine and provide a beefier 240 volts for those heavy-duty appliances, like your oven or your clothes dryer. So here are the literal final steps the electricity takes. From that local street transformer, it passes straight into the electric meter on the side of your house, which is just tallying up your usage. From there, it enters your service panel, the breaker box that's probably hanging out in your basement or garage. This is your home's own internal safety checkpoint. If a wire suddenly draws too much current, the breaker trips immediately, isolating the danger. Finally, the electricity flows through the hidden wires in your walls, waiting quietly right behind the outlets and switches for the exact moment you need it. Now, here's the part that honestly just blows my mind. The grid doesn't really store this electricity. It balances it in this incredibly delicate, continuous flow. Generation has to match consumption perfectly, in real time. The exact moment you turn on your TV, a generator hundreds of miles away actually feels that microscopic increase in load, and it has to work just a tiny bit harder to instantly supply it. It's all connected.
So, what does this all mean for the future? As we plug in millions of electric vehicles, build out these incredibly power-hungry data centers, and transition to intermittent renewable energy like wind and solar, how is this century-old, carefully balanced grid going to evolve to handle the sheer power demands of tomorrow? The journey of electricity is already a total marvel of modern engineering, but its most exciting chapters might still be yet to come. The next time you switch on a light, just remember that the electricity powering your home has traveled through generators, transformers, massive transmission lines, substations, and distribution networks just to get to you. Thanks so much for joining me on this explainer today. Keep asking questions and keep learning.